Class 10 will continue with hydrocarbons. Today we will discuss methane and ethane, the properties and the preparation and the chemical reactions. Now, since methane and ethane comes under the category alkanes, now what is an alkane? We have already discussed earlier. It is a saturated aliphatic hydrocarbons containing carbon-carbon single bond. Now, why is it called saturated? Because all the four valencies of carbon atoms are satisfied with a single bond, either with the hydrogen or any other element or compound. So this is called saturated because all the four valencies of carbon atoms are fully satisfied by forming single covalent bonds. So that is why it is called saturated, and they are the least reactive among the hydrocarbons. Among the alkenes and alkynes, alkanes are the least reactive. Why? Because they are saturated hydrocarbons. Distribution: alkanes are widely distributed in marshy lands and in coal mines, and the main sources are natural gas and petroleum. Natural gas contains about 75% of methane. Marsh gas is produced by the bacterial decay of organic compounds, and then the fire damp in the coal pockets we get methane. So nomenclature we have already discussed about that. So we directly come to the preparation of methane and ethane. So in the lab preparation of methane, we use sodium acetate, and for the preparation of ethane, we use sodium propionate. So this is sodium acetate, this is sodium propionate. We react it with sodium hydroxide, an alkali, in the presence of calcium oxide, and then we heat it. So what are the products? The products are, in the first case, if we use sodium acetate, then we get methane, CH4 and Na2CO3, sodium carbonate. Similarly, when we react sodium propionate and sodium hydroxide, we get ethane, C2H6, and again the same product, Na2CO3, sodium carbonate. So this reaction is called decarboxylation. Why? Because the elimination of CO2. This is CO2, okay? COO means CO2. So the elimination of carbon dioxide or CO2 is known as, from the molecule of in the form of carboxylic acid. So now from the carboxylic acid, there is an elimination of carbon dioxide or COO group. So this is known as carboxylation. So decarboxylation is the elimination of molecule of CO2 from a carboxylic acid. That is called decarboxylation. And the other way, now how do we collect methane and ethane respectively? Since methane and ethane both are insoluble in nature, it doesn't dissolve in water, so therefore it is collected by the downward displacement of water. Now, the general methods for preparation of methane and ethane from the alkyl halides, methyl iodide and ethyl bromide, or bromoethane or iodomethane. Okay, from methyl iodide we react it with nascent hydrogen. So when we react it with nascent hydrogen, then we get methane, CH4, and hydrogen iodide or HI, hydroiodic acid. Similarly, when we react another alkyl halide, that is ethyl bromide, with nascent hydrogen, what are the products? C2H6, ethane and hydrogen bromide or hydrobromic acid. Okay? Now, the last way, this process is known as Wirtz reaction. The Wirtz reaction is possible only if we want to get hydrocarbon with 2 carbon atoms or 4 carbon atoms, or carbon atoms, hydrocarbon with even number of carbons. Okay, even number of carbons like C2, C4, C6. Hydrocarbons containing 2 atoms of carbon, 4 atoms of carbon, or 6 atoms of carbon. Okay, so This is called the Wirtz reaction. So Wirtz reaction is the most suitable for preparation of alkanes with, is not suitable for the preparation of hydrocarbons with odd number of carbon atoms. So CH3I, methyl iodide, same thing, the same substance, methyl iodide plus sodium. So what do we get? We get ethane. The first hydrocarbon with alkane with 2 carbon atoms, C2H6 plus NaI, sodium iodide. So this is called the Wirtz reaction, which is not possible for those hydrocarbons with odd number of carbons. It is used only in the preparation of those hydrocarbons having even number of carbon in it. So these are the equations for the preparation of methane and ethane in the laboratory. Now we come to the physical properties of methane and ethane. So first property of methane is it is colorless, odorless and tasteless gas. Okay, it does not have any color. Solubility, it is almost insoluble in water. So these are the two. You've got to remember only the two properties of methane and ethane or the alkanes. It is insoluble in water, it is odorless, tasteless and colorless. Is it okay? Now, alkanes, the type of chemical reaction now. We come to the chemical properties. So when we come to the chemical properties, first thing we must know is alkanes, or in this case, we are talking about especially methane and ethane. Alkanes undergoes substitution reaction. It undergoes substitution reaction. So when methane reacts with chlorine, when methane CH4 reacts with chlorine in the presence of the ultraviolet radiations or at around 200 degree Celsius, or when we heat it up to 200 degree Celsius, or maybe at a certain temperature. So ultraviolet radiation, I think it's enough, or you heat it to some extent, then methane will react with chlorine to form methyl chloride, CH3Cl plus HCl. This is called a substitution reaction. I'll further explain this. Methane by using the structural formula, then I'm sure you will understand. So methane CH4 plus chlorine under the UV ray, what happens is any one hydrogen, it has 4 hydrogens in it. Methane has 4 hydrogen. We are having a single bond obviously. So one hydrogen will be substituted by one at a time. One hydrogen of this methane will be substituted with chlorine. So what is formed? Methyl chloride. So CH3 methyl and chloride. This hydrogen will be substituted by chlorine and then we get HCl. So this is a substitution reaction. So further, the substitution reaction we talk about Cl. This is methyl chloride. Methyl chloride further reacts with chlorine under the same conditions to get dimethyl chloride. Now what is dimethyl chloride? So we already had this. This is chlorine and this is hydrogen, isn't it? This is methyl chloride. Now one more hydrogen will be now again be replaced by one atom of chlorine. So Cl to form and of course HCl is formed. So this is called dimethyl chloride or dichloromethane. Is it okay? So now similarly, every time it reacts, what happens? One hydrogen atom will be substituted by chlorine here. So this is a very good example of substitution reaction. So now I'll continue with I will not continue with the molecular formula. Now we'll continue with the I will continue with the molecular formula and not structural formula. So this is what happens. CH3, as I had already explained, CH3Cl monochloroethane plus chlorine. Under the same conditions, what do we get? one hydrogen becomes less, that is 2, and one chlorine will get one hydrogen will be substituted by chlorine, and you get 2 chlorine atoms now, CH2Cl2 plus HCl. This is dichloromethane. Similarly, dichloromethane CH2Cl2 further reacts with chlorine to form tetrachloro. So one hydrogen less, so out of 2 only one will be substituted with chlorine, so you will get CH, Cl, now one more chlorine, so it becomes Cl3. This is chloroform. This is chloroform plus HCl. Similarly, now the last reaction here in the substitution reaction of methane, CH3Cl3 plus chlorine under the same conditions of UV and or heat, we get tetrachloromethane. All the hydrogen will be now, there's one hydrogen left, so this hydrogen will also be replaced by substituted by chlorine, so there will be no hydrogen left, so all the hydrogens will be replaced by chlorine. So CH4 we had, now we get CCl4, so CCl4 and HCl. So this is the substitution reaction of methane. So now we'll come to the substitution reaction of ethane similarly. Okay, we'll come to the substitution reaction of ethane, and we get the same products and the conditions are the same, UV ray. So we come to C2H5, C2H6 plus Cl2. We'll start with ethane. So again, what happens is one hydrogen atom will be replaced by one chlorine, substituted by one chlorine. So you get C2H5Cl. This is monochloroethane. Now in this next case, C2H5Cl reacts with chlorine. Again, there is a substitution reaction. Out of 5 hydrogen, one will be replaced, so you get one hydrogen will be replaced, so therefore you will get one hydrogen more less, so C2H4Cl, one Cl will get one hydrogen will get substituted, so one Cl more is added, so we'll get dichloroethane. Now dichloroethane further reacts with chlorine to form tetrachloroethane, C2H3Cl3. So tetrachloroethane. So tetrachloroethane C2H3Cl3 will become this is trichloro, now becomes tetrachloro. This is trichloro, 3 chlorine. So tetrachloroethane now, C2H minus 1 means 2 and plus 1 means in chlorine 4 plus HCl. Similarly, at the end, what do we get? All the hydrogen will be replaced by, all the hydrogen of ethane will be replaced by chlorine. So we get hexachloroethane, CCl6. Okay, so this is substitution reaction. So now, as we all know, the oxidation, we'll come to the oxidation now. So we all know that any hydrocarbon burns, what are the products? The products are carbon dioxide and water vapor. Like during respiration, the food reacts with glucose or the glucose to form carbon dioxide and water vapor. Similarly, any hydrocarbon burns to form carbon dioxide and water vapor. So here also methane and ethane. If you can refer to page number 230. So methane burns in oxygen, excess of oxygen. If you have enough oxygen, so we get oxide of carbon, that is carbon dioxide and oxygen. Whereas if you have insufficient oxygen or insufficient air, we get carbon monoxide and oxygen in both the cases, whether you burn ethane or methane or ethane. If you have enough sufficient oxygen, we get carbon dioxide and water vapor. If it is insufficient, in both the cases, we get carbon monoxide and hydrogen. Water. Now next reaction is by the by using, let's say, a catalyst, okay, by reacting with a substance. Now, so the catalytic oxidation, we call it a catalytic oxidation of alkanes. So catalytic oxidation, what is a catalyst? We all know that a catalyst is a compound which alters the rate of chemical reaction, but itself does not take part in the chemical reaction. So now we are oxidizing methane and ethane, CH4 and C2H6. Methane and ethane, we are oxidizing it, reacting with oxygen in the presence of copper as a catalyst. In both the cases, the catalyst is copper at 200 degrees Celsius. In both the temperatures are 200 degrees Celsius in both the equations. So we are oxidizing methane and ethane in the presence of copper at 200 degrees Celsius. Now, what are the products? The product will be the catalytic oxidation of methane in the presence of copper. Obviously, copper is the catalyst here. So we get ethanol, we get an alcohol, ethanol, methanol and ethanol in both the cases. So CH3OH and C2H5OH, we get ethanol. Methane forms methanol, ethane C2H6, ethane forms ethanol. Is it okay? So this is the catalytic oxidation of methane and ethane when copper is used. So now we have another catalyst, that is molybdenum oxide. We have molybdenum oxide. Okay, the same reaction, but oxidation, but we have molybdenum oxide. Molybdenum oxide. At the temperature, in both the cases, it is 350 degrees Celsius to 400 degrees Celsius. So 350 to 400 degrees Celsius, both the temperatures. Sorry, it's not 400, it is 500. I got confused here. So it is 350 to 500 degrees Celsius. It's not 350 here and 500 here. It's 350 to 500 degrees Celsius in both the cases. So methane and ethane is oxidizing in the presence of molybdenum as a catalyst in both the cases at the temperature of 350, somewhere between 350 degrees Celsius to 500 degrees Celsius. Then what is the product? In this case, we have an aldehyde, that is nal group, methanal. So methane forms methanal, CH3CHO. This is methanal, CH3CHO. Now, oh sorry, this is ethanol. I'm so sorry here. Ethane becomes ethanol because C2, this chalk is CH3CHO. This is ethanol and this is methanol. There's only one carbon, so HCHO. This is methanol. This is methanol and this is ethanol. So methane in the presence of oxygen oxidizes, obviously in the presence of oxygen, and with a catalyst molybdenum oxide to produce methanol, and ethane, similarly we get ethanol. Now if we have the series of oxidation, controlled slow oxidation in the presence of K2Cr2O7. Now K2Cr2O7, please remember potassium dichromate, so CH3 in the presence of the catalyst K2Cr2O7, it's a slow oxidation in the presence of nascent oxygen. Then first product will be alcohol, so CH3OH. Further oxidation in the presence of K2Cr2O7, potassium dichromate, then we'll get the product will be HCHO. Methane becomes methanol, methanol becomes methanal, methanal becomes methanoic acid. So HCOOH in the presence of K2Cr2O7 in the presence of nascent oxygen. So this is called slow controlled oxidation using the catalyst potassium dichromate in the presence of nascent oxygen. Methane produces methanol. Methanol further oxidation produces methanal. Methanal further oxidizes to form methanoic acid. Similarly, ethane C2H6 is in the similar conditions. In both the cases, we get C2H5OH. Okay, methane becomes methanol. Methanol further oxidizes to form methanal CH3CHO, produces further to form methanal CH3CHO, and then we get ethanoic acid or acetic acid, that is CH3COOH. Okay, so this is the slow oxidation, catalytic oxidation in the presence of potassium dichromate and nascent oxygen. Once more, methane becomes methanol, methanol becomes methanal, methanal becomes methanoic acid. Similarly, ethane oxidizes to form ethanol, ethanol further oxidizes to form ethanal, and ethanal further oxidizes to form ethanoic acid or acetic acid. So this is all about alkanes, methane and ethane. Okay, so if you have any further questions, you can always contact me anytime. I hope you've understood. Bye for now.